If you stand outside on a hot summer day and feel the blast of warm air coming from an air conditioning unit, it's easy to assume you know exactly what's happening. The logical assumption is that the machine is simply sucking the hot air out of your room and blowing cold air in from the outside. But that assumption is incorrect. An air conditioner never actually exchanges air mass between the inside of your building and the outside world. Look at this wireframe of a standard room and an exterior wall. The air circulating inside your room and the air circulating outside are in two distinct, isolated loops. They never physically touch. Instead of moving air, the system relies on this independent circuit that bridges the gap between the indoor and outdoor environments. Inside this closed loop is a specialized working fluid. For most modern systems, this is a chemical compound known as R32 refrigerant. The engineering challenge of an AC unit is figuring out how to move thermal energy against its natural gradient, taking heat from a cool room and pushing it out into a hot summer day. To do that, the system has to continuously manipulate the physical pressure and phase state of this R32 fluid. This setup functions as a thermal energy transportation system, utilizing the principles of the vapor compression refrigeration cycle to relocate heat without any mass exchange between the internal and external air. To track how this cycle moves heat, look at the pressure enthalpy graph on the right. We'll plot the refrigerant state as it moves through the hardware on the left. We begin outside at the compressor. Low-pressure gas enters, plotted here at the bottom right. The compressor applies mechanical work to forcefully squeeze the R32, reducing its volume. This friction and compression cause the pressure and temperature to spike dramatically, shooting the fluid state straight up on our graph. By the time the gas exits the compressor, it has reached a scorching 70 to 80 degrees Celsius. From there, this highly pressurized hot gas is pushed into a winding copper path known as the condenser coils. These coils are made of copper because of its exceptionally high thermal conductivity, allowing it to transfer heat very quickly. Here, a large fan draws the ambient summer air and blows it directly across those copper coils. Even if it's a sweltering 40 degrees outside, the compressed R32 inside the coils is still significantly hotter at 80 degrees. Thermal energy flows from hot to cold, naturally rejecting energy outward. As it loses heat, the R32 condenses into a high-pressure liquid. On our graph, this tracks horizontally left, leaving us with a liquid at 50 degrees Celsius. The massive electrical energy required to run the compressor serves one specific purpose: to make the refrigerant hotter than the outdoor air, artificially forcing the heat to be rejected. We now have an obstacle. The liquid R32 is sitting at 50 degrees Celsius. That is still far too hot to cool down the inside of your living room. The solution sits just before the indoor unit, in a component called the expansion valve. Physically, the expansion valve is incredibly simple. It is a purposefully narrow orifice, a strict bottleneck that severely restricts the flow of the fluid. When the high-pressure liquid is forced through this tiny restriction, it undergoes thermodynamic throttling. Once it passes through the bottleneck, it enters a wider space, and the pressure plummets straight down. Because the pressure drops so suddenly, the liquid becomes unstable, instantly flashing back into a gas. This flashing absorbs internal heat energy. Consequently, the temperature of the R32 mixture drops rapidly, falling from 50 degrees down to 16 to 30 degrees Celsius. This pressure drop dictates the boiling point of the fluid, priming it to absorb ambient heat from its surroundings as it enters the next stage of the cycle. Now this cold, low-pressure mixture of liquid and vapor is ready to enter the indoor unit, specifically moving into the evaporator coil. Inside your room, a blower fan continuously pulls your warm room air through a filter, forcing it directly across these freezing copper coils. Because the coils are much colder than the room, thermal energy moves out of the air and transfers right through the copper into the R32. As the R32 absorbs this heat, it reaches its boiling point. The low-pressure liquid begins to boil completely into a gas, absorbing massive amounts of thermal energy in the process and closing the loop on our graph. But there is a secondary consequence to running warm air over a cold surface: dehumidification. When the warm, humid air in your room makes contact with the cold metal coil, it hits its dew point. The air physically loses its capacity to hold moisture. That ambient humidity condenses into liquid water droplets on the outside of the coil, dripping down into a pan and draining out of the system entirely through a separate pipe. The indoor unit is acting as a thermal sponge. It wrings both heat and moisture out of your air, loads that energy into the R32, and blows the remaining dry, cool air back into your living space. The fully vaporized, heat-laden R32 gas now leaves the indoor unit, traveling back outside to the compressor to restart the entire cycle. This introduces a severe engineering constraint. The mechanical compressor is designed exclusively to compress gases. Gas molecules have plenty of empty space between them, making them highly compressible. Liquids, however, are incompressible. If even a single drop of liquid R32 makes it back into the compressor cylinder, it triggers a catastrophic failure known as hydraulic shock. The piston slams into the incompressible liquid, and the immense mechanical force will instantly fracture or explode the metal housing. To prevent the compressor from destroying itself, engineers use a critical safety mechanism, the thermal expansion valve, or TXV. Look closely at this schematic. A specialized heat-sensing bulb is attached directly to the exit pipe of the evaporator coil. This bulb is connected by a tiny capillary tube to a flexible diaphragm sitting on top of the expansion valve. In this real-time mechanical feedback loop, if the sensing bulb detects dangerously cold liquid R32 close to escaping, the internal fluid inside the bulb contracts. This reduces pressure on the diaphragm, pulling it up and choking the valve to restrict incoming flow. By slowing the flow down, the system guarantees the R32 spends enough time inside the evaporator coil to vaporize 100%. It relies on a purely mechanical, instantaneous reaction to keep the system running safely, without needing a single digital sensor. This brings up an important clarification about how you actually interact with the system. When you adjust your remote or wall thermostat, you are not controlling the thermal expansion valve. You aren't directly setting the physical temperature of the refrigerant either. The thermostat only communicates with the compressor, dictating its duty cycle, specifically how fast and how long the compressor runs. If you set a lower temperature on your thermostat, you are simply commanding the compressor to work continuously at high speed, pushing a massive volume of R32 through the loop to extract more heat. Because the compressor is doing more physical work, it draws significantly more electrical current, which translates directly to a higher power bill. Conversely, setting a higher target temperature tells the compressor to slow down or run in shorter bursts, vastly reducing electrical consumption. The thermal expansion valve independently manages the internal physics to prevent explosions, while you, via the thermostat, simply manage the volume of heat being transported over time. To measure exactly how much heat a system can transport, the industry uses a standard metric, tonnage. A 1-ton air conditioning unit has the capacity to remove approximately 3,500 watts of thermal energy from a room every single hour. To move that much energy, a 1-ton AC typically consumes about 1 kilowatt-hour of electricity in that same hour, though that draw is highly dependent on your thermostat settings and the ambient heat load outside. The entire machine runs on a continuous 4-step cycle: compress the gas, condense it to reject heat, expand to drop the pressure, and evaporate to absorb heat. Thermal energy is sponged up indoors through vaporization and wrung out outdoors through condensation, relocating heat out of the room. Through this architecture of pressure control and mechanical feedback, the air conditioner maintains indoor climate by overriding the natural tendency of heat to move from warm to cool areas.